Hey everyone, my name is Saniya. I'm your resident scientist. I'll be working with you this year to show you all the neat aspects of science. I was born in Pakistan, which is a country in Southeast Asia. From there, my family and I, we moved to New York, where I first got exposed to the wonders of science. My 8th grade science teacher, Mr. Steinkamp, really got me interested in science to teach all the different subjects in science like physics, chemistry, and biology. He would conduct all of these neat demonstrations and experiments where he'd blow up things and bring all these body parts from different animals like the heart and the lung and show how they work. And from there, I got really interested in science and I wanted to know and learn more about the world we live in. So I'm currently at Texas A&M University doing my PhD in Biomedical Engineering. What is biomedical engineering, you might ask? It's a discipline concerned with manufacturing and the development of medical devices, diagnostic devices, sensing devices, and other therapies that can actually improve medicine and hospital care for patients. For example, we've created things like the artificial heart or the artificial pancreas or prosthetic legs for helping people to walk. Within biomedical engineering, there are different fields of study, and my specialty that I'm more concerned with is nanotechnology. Nanotechnology was developed in the 1980s and was originally designed with the idea that we can build small machines, very, very tiny small machines, so tiny that you can't see with the human eye, that'll do work for us, especially in the respect of medicine. As a biomedical engineer in the field of nanotechnology, I work on creating and testing small nanomachines for detecting glucose in your body, especially for diabetic patients using fluorescence and lasers instead of needles. If anyone in your family, like your grandma, grandpa, dad, mom, have diabetes, you'll see that they usually have to prick themselves with a needle and get a blood out on a strip, and that's how they detect their glucose. Now, I don't know about you, but I hate needles. I don't like, hurting myself and pricking myself with a needle. So to improve that and to avoid that, patients getting hurt by pricking themselves, my research, we actually look at implanting small, very tiny glucose sensors in the skin that fluoresce in the skin or emit light of various colors when these sensors come into contact with glucose in the body. This technology that I'm helping to develop will enable diabetic patients to monitor their glucose without pricking themselves for blood that they have to put on the strip without hurting themselves at all. How small, you might ask, these glucose sensors are actually. The size of these glucose sensors ranges from 10,000 nanometers to 12,000 nanometers. And to just give you an idea or a comparison of how small that is, a nanometer is 1 billionth of a meter. And to give an idea in reality, so we can better understand, a nanometer to a meter would be like comparing a marble, a really small, tiny marble, to the size of the Earth. For example, a sheet of paper, if you just hold up a sheet of paper in front of you, it's about 100,000 nanometers thick. Unusual physical and chemical and biological properties can emerge at this, in materials at such a small nanoscale. And using these properties for our advantage allows endless possibilities for improving the way we live every day. I'm going to now give you a tour of the research lab that I work with and all the other engineers that I work with who helped me develop these glucose sensors that I was talking to you about. Hi again. Okay, I'm going to show you now our lab, the nanotechnology lab at the Biomedical Engineering department, where I spend most of my time. I'm wearing a lab coat because we're going into the lab. You want to be safe, you want to protect yourself, so let's go in. Okay, so what we develop in this lab are glucose sensors for diabetic patients. Right now, diabetic patients have to prick their finger several times a day to get blood out and put it in strips where they test glucose. We're trying to develop glucose sensors that you can actually implant in the skin and measure glucose by the intensity changes in the glucose sensors because they fluoresce. They have a dye that causes them to fluoresce when more glucose goes into the sensors. What I do is I do a lot of mathematical modeling to simulate how these sensors will actually react in the body. And this is my lab station that I work with. One of the models that I'm working with is here. Actually, it shows up on the screen. And right now it's just showing some of our glucose sensors in the tissue interface and how they're going to react. All the different colors show how the glucose changes with time. Now I'm going to introduce you to some of my colleagues that I work with who actually make the glucose sensors.
Hi, I'm Jason Roberts. I'm a PhD student in Dr. McShane's lab.
And I'm Dustin Ritter, and I'm also a PhD student in Dr. McShane's lab.
And how did you get interested in math and science, Dustin?
Yeah, so I was always interested in math and science. I guess starting in middle school and then throughout high school, I really became more interested in high school. I enjoyed my algebra classes, algebra 2, and calculus classes a lot. And I had a particular teacher, his name was Mr. Rogers. It really motivated me to, kind of pursue a field that incorporated math and science. So he was very passionate about what he taught, and I was able to, do some extracurricular type of things with him as far as math, like tournaments and stuff like that. So that's when I really became interested in math and science.
That's actually really similar to mine.
So, why did you become a biomedical engineer?
Well, I actually went into college in natural sciences, so I was thinking that I would like to be a doctor. That was my original plan, but when I actually found out that, being a doctor is a lot about just knowing a lot of material, and you don't really get to experiment at all, or you don't really get to be behind new developments. And so I chose biomedical engineering because it kind of supports the medical field, but then you get to be the person who's coming out with the new stuff and being on the cutting edge.
Okay, so are you guys going to show us what you do now?
Sure. Okay, so what we basically do in our lab is we're trying to develop optical glucose biosensors for diabetics who have to check their blood sugar numerous times a day. So the recommended testing frequency is about 4 to 7 times per day, which tends to be a lot because the diabetics have to prick their finger and draw a glucose sample, and then once they draw the glucose sample, they put that into some kind of testing apparatus, and it'll give them back a glucose reading. But what we're trying to do is make something that is going to be minimally or non-invasive, meaning that they don't have to actually puncture their skin and draw blood samples, and it can also be continuous. So that's the idea. What we do in this lab to get to that goal is we make microparticles. These microparticles are porous, and we're able to load them with certain sensing reagents. So we use some enzymes, which are just proteins, and we also use some fluorescent dyes. So I think Jason is going to talk to you about the making particles, and then I'll explain briefly how we load them with the enzymes and the dyes, and then I'll also talk about how we test the sensors here in our lab.
Do a little bit about how we make the particles. So our particles are algilica, which is a mixture of alginate and silica, which the alginate is this powder right here, and the silica is in this liquid right here. We combine the two in a beaker and stir it, and then the particles form in that liquid, and we kind of solidify them using a base, ammonium hydroxide. I'll show you here, we're actually right at that point, and we need to add it. Because the particles are so small, we use really small volumes of liquid, and we have to really control how much liquid we add. So we use something like this. You can see the syringe here and this machine, which we'll start right now, drops the liquid at a steady rate so we can get it in there in a controlled manner. And this will have to go for at least another few hours. But in the meantime, I already have some made up, which you can see right here. It looks just like a cloudy liquid. You can't see the particles at all just because they're so small. But in a minute, Saniya will take you over to our microscope where I've put some of these on a slide, and we'll be able to see them easy.
Okay, so now I'm going to show you what we do after Jason actually makes these alginate particles. We come in here in this lab. There's a microscope here. This is a light microscope that has a camera attached to it, which sends pictures to this computer interface right here, where we can actually view what the camera sees through this microscope. And like Jason mentioned, that these alginate particles are really, really tiny. They're actually approximately 10 to 40 micron size. So they're too small for the human eye to see it. That's why we need to use this light microscope to see them. This light microscope actually magnifies these micron size alginate particles to 300 times more than the human eye. And then the camera sends the pictures to this computer where we actually see what the alginate particles look like. Here you can see that they look like circular figures, and this program actually allows us to exactly measure how much they are, which I've done here, and this is about 100 microns. So two particles are taking about 100 microns of space. In the beginning, I mentioned that these alginate particles are infused more with glucose oxidase, which is an enzyme, and it becomes a glucose sensor and gets implanted in the body. And the way we measure glucose is that the sensors that are implanted in the dermis, they actually fluoresce, and they fluoresce different intensities based on how much blood glucose is present. And the after final math of how these actually look when they fluoresce is this. This is a lot of alginate particles all together, and they fluoresce green light.
And so once we actually make the sensors here in the lab, we have a number of different instruments that we can use to test the sensors that we made. So this is an example of one instrument that we use. It's called a spectrophotometer, and it allows us to take our sensors and measure the fluorescence that they give off. So we shine a certain color of light on the sensors, and they emit fluorescence, and we're able to detect that fluorescence. We have a particle size analyzer, which is behind us here, and basically we can put the particles that Jason makes before or after we load them with an enzyme in the dye, and we can find out exactly how big they are and what concentration they are. But then one of the most important systems that we have in our lab is actually used to test the glucose response of our sensors in vitro, and this system here. So this system allows us to take our particles and immobilize them inside a flow cell that we can actually flow glucose solution across the sensors, and at the same time we can shine light on the sensors and collect the fluorescence just like we do in the spectrophotometer. And so we have this custom created program that allows us to automatically shine the light and collect the fluorescence and control all the glucose concentrations all through this one program. So we're also able to control, by using an incubator, the temperature that the particles are exposed to, and we have a number of gases that we can bubble in to control the oxygen concentration. So all of these things allow us to more carefully control the environment that our sensors are exposed to, so that we can closely match it to what they would see in a physiological environment.
Okay, so now I'm going to introduce you to my advisor, Dr. McShane, who I go to for advice on my research. If I ever have a problem or I'm stuck on my research, this is the person that I go to for information and help.
Hi, I'm Dr. McShane. I'm Saniya's advisor, and that means I help her do her research, give her the problems that she is working on, and also help her pick her classes that will prepare her for her future, both in her research now, but also for the job that she'll have someday when she leaves here. So I have a PhD in Biomedical Engineering, and that means I went to school for about 9 years after high school. So I mentioned that I help her choose classes and I give her the problems to work on. I guess the primary thing is I give her a problem to work on, and then I give her the tools to work on the problem. So in her case, because we're working on these implants, we have some questions about how the body responds to these foreign materials. And particularly because we're designing implants that respond to biochemistry inside the body, where she is modeling the transport, which means the movement of these small molecules from the blood vessels into the tissue where the implants would reside. And she's doing that using mathematical models that are that require, let's say, lots of computing power. And so I give her a powerful computer and the software that is already set up to solve these complicated equations. And it does it in a format that allows her to essentially draw what she wants to model using a CAD type of computer-aided design type of software. And then she tells the computer program what equations apply in different situations, and then tells it to solve them.